The question of what existed before the Big Bang has puzzled scientists for decades. With advancements in cosmology, some answers are starting to emerge, and they are as unsettling as they are fascinating. Renowned physicist Brian Cox has shed light on this mystery, revealing a scenario that challenges our understanding of the cosmos. According to Cox, what existed before the Big Bang was not a void of absolute nothingness, but rather something profoundly strange and deeply terrifying. How our universe was born from nothing, or if something existed before, remains a mystery. However, that is not stopping some physicists from trying to figure it out. My understanding is that nothing comes from nothing. For something to exist, there must be material or a component available. For those materials to be available, something else must exist first. Where did the material come from that created the Big Bang? What happened in the first instance to create that material? Peter O. from Australia raises an interesting point. The last star will slowly cool and fade away. With its passing, the universe will become once more a void without light, life, or meaning. So warns physicist Brian Cox in the recent BBC series Universe. The fading of that last star will only be the beginning of an infinitely long dark epoch. All matter will eventually be consumed by monstrous black holes, which will in turn evaporate into the dimmest glimmers of light. Space will expand ever outward until even that dim light becomes too spread out to interact. Activity will cease. Or will it? Strangely enough, some cosmologists believe a previous cold, dark, empty universe, like the one in our far future, could have been the source of our very own Big Bang. Before diving into this theory, let's first understand how physical matter came into existence. If we aim to explain the origins of stable matter made of atoms or molecules, we must recognize that none of it existed at the moment of the Big Bang or for hundreds of thousands of years afterward. We have a detailed understanding of how the first atoms formed out of simpler particles once conditions cooled enough for complex matter to be stable. These atoms later fused into heavier elements inside stars. However, this understanding does not answer the question of whether something came from nothing. To explore this further, let's go back in time. The first long-lived matter particles, protons and neutrons, which make up atomic nuclei, came into existence around 1/10,000 of a second after the Big Bang. Before that, there was no material in any familiar sense. Physics allows us to trace the timeline even further back to physical processes that predate stable matter. This takes us to the so-called Grand Unified Epoch. At this stage, we are in the realm of speculative physics, as our experiments cannot produce the energy levels necessary to probe these early processes. However, a plausible hypothesis suggests that the physical world was made of a soup of short-lived elementary particles, including quarks, the building blocks of protons and neutrons. There was both matter and antimatter in nearly equal quantities. Each type of matter particle, such as a quark, has an antimatter counterpart which is almost identical but different in one key aspect. However, matter and antimatter annihilate each other when they meet, converting into energy. This means that these particles were constantly created and destroyed. How did these particles come to exist in the first place? Quantum field theory tells us that even a vacuum, what we consider empty space, is full of physical activity in the form of energy fluctuations. These fluctuations can give rise to particles that pop in and out of existence in an instant. This may sound like a mathematical quirk, but such particles have been observed in countless experiments. The vacuum of space is teeming with particles constantly appearing and disappearing, seemingly out of nothing. However, this suggests that the quantum vacuum is not nothing, but rather something. Philosopher David Albert has criticized the idea that something can come from nothing in this way. Suppose we ask where space-time itself arose from. This takes us further back into the truly ancient Planck epoch, a period so early in the universe's history that our best theories break down. This era occurred only a tiny fraction of a second after the Big Bang. At this point, space and time themselves were subject to quantum fluctuations. Physicists usually work separately with quantum mechanics, which governs the microscopic world, and general relativity, which describes cosmic scales. However, to truly understand the Planck epoch, we need a complete theory of quantum gravity that unifies both. While we lack a perfect quantum gravity theory, attempts such as string theory and loop quantum gravity suggest that space and time are emergent properties. They may be akin to waves on an ocean, where what we perceive as space and time results from deeper quantum processes. One thing is certain. Physics has never confirmed instances of something arising from absolute nothingness. In the Planck epoch, our usual notions of space, time, and cause and effect break down. Yet all candidate theories of quantum gravity describe something physical occurring in this era, some quantum precursor to space-time. But where did that come from? The Big Bang is widely regarded as the beginning of our universe, a moment when the cosmos was extremely hot, dense, and rapidly expanding. We observe remnants of this event in the cosmic microwave background radiation, a faint glow visible across the sky. However, what triggered this explosive event? As Brian Cox explains, the Big Bang, the moment when the universe became hot and dense, is just one chapter in a much larger cosmic story. What came before may be even more profound, a period known as cosmic inflation. Cosmic inflation refers to an epoch in the early universe when space expanded exponentially faster than the speed of light. This rapid stretching of space-time abruptly ended, depositing immense amounts of energy into the universe. That energy then formed the particles, radiation, and matter we observe today, the events we associate with the Big Bang. The concept of inflation suggests even deeper implications. In a model called eternal inflation, the universe is part of a vast fractal-like multiverse where inflation never stops. Each patch of inflation forms a bubble universe, meaning our cosmos is just one of many. This concept raises eerie and profound possibilities. If our universe emerged from a vast, ever-changing cosmic landscape, it suggests that before our Big Bang, countless other universes may have formed, expanded, and eventually dissolved in an endless cycle. This idea aligns with the theory of eternal inflation, which proposes that inflation, the rapid expansion of space, never truly ends, but instead continues indefinitely in different regions, constantly giving birth to new universes. Each of these universes could have unique physical laws, different fundamental constants, or even entirely unfamiliar forms of matter and energy. The question of what existed before the Big Bang also challenges our fundamental understanding of emptiness. We often think of a vacuum as absolute nothingness, devoid of matter and energy. But modern physics suggests otherwise. Even in the emptiest regions of space, quantum fields continue to exist, fluctuating unpredictably due to quantum mechanics. These fluctuations generate a non-zero background energy known as zero-point energy, meaning that what we perceive as empty space is in reality a seething of invisible activity. If this is true, then the pre-Big Bang state of the universe might not have been true nothingness, but rather a dynamic, energy-rich quantum realm. This persistent energy could have provided the necessary conditions for a new universe to emerge, potentially setting off another Big Bang. Such ideas push the boundaries of our understanding, suggesting that the cosmos may be far more vast, complex, and eternal than we ever imagined. Cox emphasizes that even in the most barren stretches of the cosmos, physical laws and quantum fields remain active. This suggests that before the Big Bang, the universe was a cold, empty expanse dominated by inflationary energy. The implications of eternal inflation are terrifying. It suggests an infinite multiverse where universes continuously form, expand, and fade. Each universe could have different physical laws and constants, making ours just one peculiar outcome among countless possibilities. This leads to profound questions. Is our universe unique? Could other universes harbor intelligent life? If eternal inflation stretches infinitely into the past, does the concept of a beginning even make sense? Despite the elegance of inflationary models, they do not resolve every mystery. The horizon problem questions why distant regions of the universe have uniform temperature and density. The flatness problem asks why the universe appears spatially flat. While inflation explains these issues, it also introduces new ones, like why inflation started at all. Brian Cox's exploration of the universe's origins has sparked awe and fascination. While the Big Bang theory remains central to modern cosmology, it leaves lingering questions about what preceded it. Could something terrifying have existed before this monumental event, reshaping our understanding of existence itself? The journey to understanding the origins of the universe is far from over. As our observational tools improve, we may detect signals from the distant past, such as gravitational waves from inflation or dark matter interactions. These discoveries could redefine our understanding of space-time and reality. For now, Brian Cox's insights remind us of the profound and humbling reality of the cosmos. Something unimaginable existed before the Big Bang, and it continues to shape the universe we inhabit. As scientists probe deeper, they may uncover answers that fundamentally alter our perception of existence itself.